Thank you, Father Dr. Binay. It's a great honor for me for having been called by the college, which is one of this famous Jesuit, academia. So, and I'm very grateful for that very, kind introduction. Without further ado, let's go ahead and whatever I can. I hope that most of you, at least, a majority of the students here know the basics of thermodynamics and some aspects of radiation. So if not, you're always welcome to go through the lectures or call me again later. If you don't understand, I'm sorry, but I'll try to the best of my ability. And if you have any doubts, you could ask. Right. Most of you have heard about this IPCC, International Panel for Climate Change. So which is it's an authoritative body of more than a few thousands of scientists who go through all the books and pour the information, filter the information, and collate the information on climate change. The recent one got published a couple of months ago, the science part of it. And so let's see quickly what it says. So the human influence has warmed the climate at a rate that's unprecedented in the last 2000 years at least. Okay, if you see the picture here, you can see the sudden spurt, the right side, since industrial revolution 1850, and so on and so forth. And the right side tells you if since 1950s the jump has been phenomenal. And this doesn't happen at one go. Though you're pumping in CO2, the atmosphere takes some time to adjust, ocean store it, and again after some time it goes into a new regime or equilibrium, as most of you know. So you can see this regime jumps here, it goes on. And in the beginning of the current century, people thought that it is flattened, what you call as hiatus, but many of were thinking that it was premature, and indeed it was premature. Again, we are breaking records in temperature in terms of temperature rise. And this slide, without going into the details, it tells you, we observe that the more the CO2 is being pumped, the more temperature increase is, you can see. Well, so far so good. All of you know these things. When I say CO2, it's not only CO2, but in the greenhouse gases like methane and water vapor, they also play a major role, and they all are contributing to this. And interestingly, that's so far based on observations and model studies also. Then this question, this picture, you must be studying that, in future, if you pump in so much, so this will be the temperature, and so on and so forth. So this picture tells you a collation of many research papers, outputs. You can see that if you pump CO2 in future at a certain level, the heating would go beyond 2 degrees. But if you pump it more, it will be 4 degrees, and so on and so forth. How do we say this? We are scientists like me are now who work with climate change models. We are reasonably confident, very good confident within the limits of uncertainty. I mean, even the uncertainties are, as a global level, they're relatively less. So we are very confident, good, reasonably confident. Then how can we be so confident? And then all of you know the extreme rainfall events are increasing. Lot of cases, Chennai case, Hyderabad case, Cochin case, you had all these rains. And in urban place, this is mostly, we now believe that, our studies, climate scientist studies show that, mostly a part of this extremity, a majority of can be attributed to the increasing greenhouse gases. In addition, some of us, we have also done studies for urban extreme events, like one of my students, Boyaz and all. We show that land use, land cover, urbanization also is contributing about 10%, but predominantly our greenhouse gases are playing a major role, the greenhouse gas related warming. Okay. So this is very well known. There are many other effects, sea level rise and all. So the whole attribution studies are, they can be, Manabe has played Sukuro Manabe, with whom I had the pleasure of, the privilege of working in the same institute and having been guided by him for a paper in Japan when I was used to work. And he was the major person for one of these, most of the climate change modeling work can be attributed to him. It started with him, Then, of course, Nobel Prize for climate change was shared by Manabe and Klaus Hasselmann, and so both of them shared it half, and the other half is for the complex mathematics by Giorgio Parisi. I'm not going to talk about his work now, but they are also connected in stochasticity, etc. It's connected to climate. If time permits, I will show you some of those results. Anyway. So some of the slides were shared by Professor Dr. Krishnan, my former colleague from IITM. He also gave a similar talk. So some of these slides are from him. Okay, if you go to the website of Nobel Prize, you will see Manabe Sensei was born in 1931. Sukuro Manabe, Sensei's teacher, when we are used to call him as Manabe Sensei, 1931. Okay, then he moved to Princeton after his PhD, and then GFDL, and rest is history. And quickly, the Nobel citation tells you he demonstrated how increased levels of CO2 in the atmosphere led to increased temperature in the surface of the Earth. In 1960s, whatever research he has done on the physical models of the Earth's climate was important. He was the first person to explore the interaction between the radiation balance and vertical transport of air masses. His work laid the foundation for the development of current climate models. After 10 years, Klaus Hasselmann came up with the idea, proved that weather, which is a stochastic, most of you know what is stochastic, a random thing, predictability is less, but climate is relatively easy to predict. So, but he established that they are related, and the climate is what you call as an envelope of the weather. So then also he proposed the methods how to attribute the climate change, to a certain, driver. Then quickly a slide on this, what we call as numerical weather prediction. We use climate models. Newton's laws of motion, all of you in the school and college, you studied F is equal to ma in a non-rotating frame of reference. But once you keep the Earth's rotation, these equations become very, very complex. There are non-linear equations which have general no simple solutions. So add to that the complex atmosphere, radiation comes and each particle of aerosol reflects it. And 1 kilometer cloud, 1 to 10 kilometer cloud drive a 500 to 600 kilometers of tropical cyclones. So all these things are modeled through some physical dynamical equations. So the whole story started with Willem Biakinis in 1904, who wanted to, he knew the equations. He said that it's an initial value problem. You can solve them if you have the initial data. He proposed what is called as a weather factory with 64,000 computers at that time, means humans sitting around and transferring data and all. It's a magnificent idea, and it failed magnificently. But it was such a failure from which we could all learn. And then Richardson came. Then the failure was Richardson's failure. Bjerknes was the first guy. Richardson's weather factory idea failed, but that was a very important one. Then people understood. During his lifetime itself, he could see how it helped in giving a weather forecast in mid-latitudes. Lot of developments, maybe some other talk, how the World War helped develop this one from an art to a science. One of the forefront of physical and mathematical sciences, we'll talk later. And so the weather prediction and all started in 1950 and so on and so forth. Then some of you know about the theory of CEOAS, also Lorentz theory. All these things fed into climate modeling also. And one of the biggest, beneficiaries of computer development was our weather forecasting and climate change studies. Science-wise, all of you know Fourier, the concept of glass bowl effect that helped Tyndall propose what we call as greenhouse effect. All of you know that. So what happens is the solar radiation heat is coming, but atmosphere is permitting that, but it's not allowing it out. Okay, so at least some of it is trapped like a greenhouse. That's why the greenhouse gas effect. Then Arrhenius about, if you double the CO2, the temperatures will increase. Then in the modern era, your Guy calendar suggested that human activities would increase the temperatures. From that, it's very much Professor Keeling, Mauna Loa carbon dioxide measurements. It's a very, very important facility. Now we have one in near Goa also, but Mauna Loa facility is the global standard. Then Manabe Senses work, Manabe and Strickler, Manabe and Weatherald. That is the game-changing paper, Manabe and Weatherald. And before that, there are a couple. This is from Krishnan. There are other two works, Manabe and Moeller, and Manabe's convective scheme. I would like to add those two also as it's great contributions to climate change. Before I go further, I don't know how many of you know about that. As you go from surface, the temperature decreases uniformly. What you call that fall in temperature is called lapse rate, and beyond that, up to 10 kilometers in mid latitudes. For us, it's 16 kilometers, 14 to 18 kilometers, depending on the season and all. And then after a small pause, the temperature increases. This is called a stratosphere up to 50 kilometers because of the presence of ozone. These two layers, troposphere and stratosphere, are important for our climate. So I don't worry about the other part, but you should know these two. So Manabe and Moeller in 1961, they came up with a couple of papers based on their recent laboratory results. People have been studying by that time how the carbon dioxide permits, short-wave radiation, absorptivity of long-wave radiation, and by carbon dioxide, ozone, etc., water vapor, etc. So based on that, they come up. I mean, individually people were working it, but Manabe's greatness comes that he said, yes, we have to pull in all this information, and that is important for climate. So he came up with this idea, and if you see the standard atmosphere of, generally globally average standard atmosphere, the dashed line, Manabe came up with what is called as radiative equilibrium. What is that? Your short wave is coming, long wave is going, Earth is emitting a long wave radiation, and the atmosphere is trapping it. After some time, there is an equilibrium. Because it's fundamentally radiation, it's radiative equilibrium. So based on their arguments, they could define what is called as this radiative equilibrium curve. And there is this what is called as dry adiabatic lapse rate. If the temperature at which that, as you go up, temperatures fall, as you go up, the temperature decreases at 6.5 degrees per kilometer. If it's a dry condition, that's dry adiabatic lapse rate. You are lifting the air parcel, dry adiabatic. If it is moist processes are involved, it will be 4.3 because moisture condenses, latent heat is released. Anyway, so based on this, when they have done that, this is the first one you can see. They could get this structure, though they didn't get the tropopause, it's decreasing and it's increasing. Importantly, their atmosphere was very, very cold. Troposphere was cold, but still they could get this structure, okay? So they also got a low tropopause because they realized that there is no latent heat release, moisture condensation, etc., etc. Okay. Before I go further, most of you have studied Wien's law and Planck's law and Stefan Boltzmann's law in radiation, BSc level, I'm sure. So the solar radiation, among other waves, the sun that's important for us at the top, outer layer of sun, about 6,300 or 6,000 Kelvin. And Earth emits at 6,000, Earth's temperature, average temperature is 288 Kelvin. So what you see is at this rate, if you see your Planck's law and Stefan Boltzmann, or you can use all Wien's display law, wavelength is inversely proportional to temperature, you will come that there is a certain wavelength at which sun emits and Earth emits. So Earth normally emits a long wave radiation because the temperatures are cold, and solar radiation, you will see around 0.4 degree visible radiation is what we get. Okay, so this Earth emitting in 4 microns to 50 micrometers, this is very, very important for greenhouse effect. Okay, as somebody said, where the action is. Okay, what happens is when the incoming solar radiation is there, visible radiation is there, we have this our gases CO2 and H2O and O2 and O3. This particularly H2O and water vapor actually. So these are very transparent. They will not disturb visible radiation. It comes down. But once the Earth starts to emit at its own temperature infrared radiation, these things start capturing them, absorbing them. Water vapor has a band of 6.3 peak. It absorbs there the radiation at 6.3, and carbon dioxide absorbs around 15 micron. And there is an overlap between some of these. Even here, you can see water vapor also has some absorption here, and ozone has its own band, and so on and so forth. In summary, all these gases are not permitting the emission of your infrared radiation. That is long wave radiation from the earth is not permitted to go out straight. Some of it is absorbed, and because their the inherent property, some of it is again radiated back. So that's the story, most of greenhouse effect. So Manabe and Moller came up with, for the first time, they put it in a mathematically, what our observations showed in lab. They said that at any level, long wave radiation can be taken as incoming minus outgoing. A difference between them, they have taken this one. And they also put an equation. This rate of change of temperature is not only directly, it's a sum of all the gases, water vapor, carbon dioxide, and ozone. They came up with this equation. Though this partial difference, all those math, I am not going to tell that, but it's not that simple, because there is so much of infrared, there is different frequencies. And if you take a point, there is a lot of radiation that is coming at different frequencies, and there is a diffuse radiation coming from all sides. It's not only from here, right? It can take the radiation from surroundings. So it's a very complicated process, and they had to do that in simplest possible way. You can't put each aerosol, even though you can't do that. You can never do that. So you have to vertically integrate along the height and along the frequency, plus at each height, each slab, you have to do that, at least at levels that you are interested, your model level is there. So this is a very complex math, but they have given life to that. They proposed all this math, and they did that. Whatever we saw that profile, that was a manifestation of their result. Then this thermal equilibrium. Yes, there was cooling. The troposphere was very cold. So Manabe and Strickler came up with, what you call as, this is Manabe's brainchild actually, a convective adjustment. What happens is when the moisture is pumped up, as it goes up, once it reaches a certain level, it becomes saturated enough. The air becomes saturated, and then moisture is released as rainfall. And when it happens, there is a phase change and latent heat releases there. In fact, in tropics, that's the main driver for us. Okay, so this was not there before. They said that this is important, and they tried to add this component. And another important factor in this paper is they have what you call as, they have defined ozone effect. So anyway, while doing that, they also said that all these things will come to equilibrium. See, if you see the middle picture, if you have a profile only with H2O and CO2, there is continuous cooling. But you add the ozone in mid levels around 100 millibars, 10 to in the stratosphere, lower stratosphere up to 20 kilometers or whatever you say, 20 to 30 kilometers, this warming happens. So this was a great finding. They also found that as the cloud height increases, what type of radiative balance happens. This is all at a single point they're doing. They are not taking the global model like we do. At a single point, they're checking the physics of this one. And this is the complete equations of motion. Some other time, there is not much time, but there is, zonal wind and meridional wind, horizontal winds and continuity equation, your thermodynamic first law, and H by Cp is your diabatic heating, clouds and radiative, and moisture equation you need. If you're an ocean modeler, you will replace this with salinity, and so on and so forth. All this led to their first, till that time, they were talking of limited area model. Computations were very bad. So limited area model, but they proposed a global circulation model prototype. Smagoronsky, his boss, and he, okay? And with that, they could get global climatology for the first time, reasonably, whatever little data they had from observations they have constructed, and there was this tropopause, many of the features were there. Only thing was it was slightly cooler, the top one, but it was okay. Not only that, importantly, they got this direct and indirect cells. So for the tropics, what you have Hadley cell, but a lot of the energy transfer to mid latitudes is, what you call as the synoptic disturbances, eddies in time and space. So they go and they sustain the climate in mid latitude energy. We are getting solar radiation, not them. So all this sort of thing, they could propose in this, they could get this from this model. very well. And Manabe's convective system, personally, I think it's as good as radiation scheme, any other contributions of Manabe. So they proposed, what happens, the lapse rate, it's very difficult to model these things. Even if you have 1 kilometer, now we are able to simulate explicit rain and all now at 1 kilometer and 5 kilometer resolutions. But even now it's not so easy. So they came up with this beautiful concept. Whenever the lapse rate is, as the parcel is going up, it's cooling up. But if it is if the way you exceed a certain amount of lapse rate, diadiabatic lapse rate, then that means whatever temperature is there, it has to be readjustment should be there. Similarly, if you are lifting the parcel, air parcel, and it is getting saturated at one level, you release it. So they put, so otherwise you will get funny lapse rates. The moisture has to go. So this is, that's the rainfall. It's a very, very simple concept, but brilliant idea, So till recently, till early 21st century, many models use this, or its variant. And this is what I said is the game changing for climate change is Manabe withdrawal 1967. They still use this simple radiative convective model. Those of you who studied your thermodynamics, CPT by a temperature change, internal energy plus, work, you divide the energy. So this is the whatever diabatic change is the temperature, it's radiation plus convection. So they have done that. In this process, for the first time, they have done that. We'll keep the relative humidity of the atmosphere doesn't change over a season. Relative humidity is vapor pressure by saturated vapor pressure at that particular temperature. With that philosophy, they have their convective adjustment, everything fell in place, and for the first time, they doubled the CO2. What happens if you double the CO2? And they found that, if you double the CO2, you will raise the temperature by 2.36. So from India, our first Earth system model, climate model, with which I was also associated, I was leading the first version of that model. Anyway, so that they have contributed to IPCC. We get some of the scenarios in Krishnan's group, gets it 2.3 degrees doubling of CO2. And these results, Manabe has done with a simple model. We are doing fastest computers and very, very complex models. We are getting similar values. Of course, these values do change from model to model, but he got this figure at that time. 1967, it's imagined. So then with that, this is the picture he has come up and showed. If you have 150 to 300 millibars, 300 to 600 millibars in the surface, the values are, you can't see the 2 degrees, but if you see that the red color is much higher than this blue color now. And as you go up, the stratosphere actually cools. Even they got that. So then technology, data, and computers are improving. So Manabe and Weatherall, they went to what we call as now 70s. By 70s, they got faster computers. Till that time, their job was actually not so much to do the climate thing, but they wanted to see the effect so that they can do a lot of other works, simple physics, because computer resources are very less and convection is also important for weather forecast. They were doing all those things. But slowly, once they realized that doubling of CO2 increases temperature, they started this 3D model atmosphere. First time they coupled atmosphere to ocean. Most of you know that atmosphere has, it warms fast, cools fast. The coefficient of, what is the term that, the coefficient of thermal conductivity, whatever you call that, for ocean and atmosphere, they're different. So ocean warms late, loses heat late. So that ocean is the memory of the climate, actually. So they coupled the ocean and atmosphere for the first time. At least they tried to link. It's a swamp ocean model. Basically, they prescribe sea surface temperature at every point. There is no ocean current. Most of us even still do that to see the simple effects of ocean. We make this type of experiments. And so in 75, they started doing that. They have this, all the equations of motion I have shown, and they have put very simple, interactions, ocean atmosphere there. Just fluxes are there. There is no ocean current transferring the heat and all. They knew that this propagation in the earlier papers, they said that transmission to mid latitudes and all transport is important. We don't have time, so I'm not talking about that. In this paper, again, they confirmed what they claimed from the simple model, CO2 doubling, causes your, increase in temperature, and that in the stratosphere is cooling. For example, here in this picture, you can see the blue color is all cooling, and this yellow color mostly it's warming in the troposphere. Not only that, they said this hydrologic cycle increases, what we call as extreme events. So these sort of things are also, they have worked on all these sort of things. So because of warming and consequent heat increase, what happens is, in simple terms, the argument is, as the temperatures increase, the ability to keep saturation vapor pressure increases, and then you can retain more moisture. Atmosphere can retain more moisture. Once it's saturated, all that falls down, and it takes more time to pump in heat. So this is an impact of climate change many of us believe happens. There is some opposite effects are also, not going to talk. This is what is basically known as Clapeyron equation effect, effect. So Manabe, and there are many hundreds of studies now. All of you must be studying in newspaper about the individual effect. At that time, the model was so simple. This is supposed to be United States, and this is sea, neighboring, Pacific and all. But that was their model. In this model, now we run models at climate change projections are done at 30 kilometers and all routinely. So all this culminated Manabes. You can see how that has motivated people. Based on that, people started giving this assessments, and then climate change policy. I was also involved in many of these things till I came to university. And this you can see the observed warming of more than 1 degree since industrialization. You can see 1.1 or something, 1.2, and then out of which the total human influence, warming because of greenhouse gases, cooling because of some of the aerosols, not all aerosols, but majority of aerosols cool. So this picture tells you the recent one. So all this started with Manabe's ideas, and then future projections also using the models. We now, okay, in the next 100 years, what happens if we go on increasing the CO2 by say certain percentage, or after 100 years it doubles or quadruples. So now many of you have seen that in the newspapers, the discussions on 1.5 degrees, 2 degrees, and 4 degrees. There is a lot of disagreement across the models, but some of the signals, the disagreement is amount of signal that you get. But in general, particularly the warming and all models do agree, and we are getting some skills in, impacts on the rainfall also. There is reasonable, some confidence. You can go to IPCC website, ipcc.ch, download summary for policymakers. You will read all of that. That will be interesting for you. And there is a lot of other material. In Manabe, since Professor Manabe didn't stop there itself. He came up with a lot of other ideas. Monsoon, your Himalayas and Tibetan high, the role of that, without going into much details. The Tibetan high is, it's up elevated. What happens is, mostly it's dry, so a lot of sensible heat is there, and it heats up, and after it goes up, but after some time there will be anticyclonic circulation that comes out, and that is coming towards, and you're all from Kerala, the monsoon onset, how the monsoon comes up. So this whole circuit of monsoon coming from surface and going up like this, the mountains play a role. If Himalayas were not there, all these things. Now we say Himalayas are not there, what would happen? Probably the monsoon would go forward. Manabe and Han and Manabe, this was the first paper that they have done that using these models by removing in your model equations, wherever topography is there, you remove that, and then what happens? This is what they have done, and they said that these things are important, and many of these motivations. This work has motivated many people. Later on, Professor Bhaskar Rao, my professor, has done some experiment. Even now, we have done one of my PhD students for paleo, last 1,000 years before, how the Tibetan high played a role in monsoon variations. Some work has been recently, my student Charan has done his thesis. And another important thing is Manabe's contribution is, some of you have heard of this thermohaline circulation. Ocean, this red color and blue color. One is, the warm waters go and subside in North Atlantic. They start in the blue color. The globe goes around the ocean, around a few hundreds of to thousands of years of variability for the water once it seeks to come out somewhere. Okay, it comes, and by the time it comes back, the circuit, a few thousands of years. or a thousand, and so this Manabe suggested in 1991 itself. This is called as thermohaline. Haline means salt. So it's not only temperature but salinity. Salinity plays a role. If the density, if density differences are there, higher density water sinks. So based on that, this thermohaline circulation was, scientists have found that, interpreted it, and Manabe using the models, and he said that if you double the CO2, your thermohaline, I'm very sorry, thermohaline circulation weakens. Okay, so in 99, they have Stauffer and Manabe again revisited this problem with a better model, and they have done that. And not only that, they have said, what would happen if the CO2, if you are pumping CO2 suddenly, you pump so much, rather than that you are pumping it slowly, you're not allowing the atmosphere to settle edges, what would happen? And they came up with very interesting suggestions. For example, if you are going to pump CO2, you pumped 100 units in 10 years, you pumped 100 units in 100 years. So that at the end of that 100 units, when you have done this 100 years in the later case, the effect would be worse. Okay, so the weakening will be of thermohaline circulation will be much worse. So this type of things. There was a movie called Day After Tomorrow. Some people say that this is based on some of these studies, actually, but there is a sign difference. It should have been warmer, but everywhere it's freezes. But that attract, these type of theories attract common people also, because they're really relevant for people, And I have finished 40 minutes, Professor Father Binoy.
You have finished almost 40 minutes, almost. Yeah.
Okay. So let's let me talk for a few more minutes.
Then we may move into discussion after.
Yeah. There is, some of you know what is El Nino. Warm El Nino, Eastern Pacific is always cool, and Western Pacific is warm above the convective threshold. So there are always clouds. So this is the normal conditions in Pacific. But once in a while, Eastern Pacific warms. So traditionally fishermen, and because of that, warm water, cold water, when it's cold, upwelling takes place, nutrition comes, they used to catch fish. But during El Nino, which this condition, what happens is, there is less upwelling, so less nutrients, less fish catch. So traditionally, Peru fishermen used to call that as El Nino, because this peaks in December. El Ninos, basically the child, in association with Christmas, they used to call that El Nino, boy conditions. But the opposite case is the name La Nina. Scientists gave it in 1960s. The opposite condition is you get more. It's more of a normal condition. And this El Nino is very important. Whenever El Ninos happen, conditions from Indonesia all the way to India, we get, many of us know that El Ninos cause dry conditions over India. And we discovered a different type of El Nino, what we call as pseudo El Nino or El Nino Modoki. Anyway, whatever El Nino you take, Manabe has also worked on these aspects. He said that slow changes in El Nino, based on some paleo observations, can be, and in late 90s, they said El Nino's slow changes are there, and it's because of global warming. Initially showed that using long experiments, they said that no, this can be because of natural variability also. Natural system has that. They also came up, I think this is all high level, maybe you don't understand that, but this is one of the studies that motivated me. That's why I'm quickly showing it. So they said that there is a decadal variability in the tropics, and this may be because of global warming also. So there is natural forcing, there is global warming. So whatever Manabe said, if any changes, it's not just global warming. He was talking a lot about past climate also. These type of signals are due to natural variability also. And based on all those suggestions, now we can very confidently say anthropogenic effects are not just natural, but recent warming is because of anthropogenic effects. Natural signal is there, but it's much less. But all these thoughts emanated from these guys. So then based on that, I have done my own work on Indian Ocean dipole. Indian Ocean also has shown this type of decadal variability, what we call as Indian Ocean dipole, another phenomena, which I showed that its impacts on monsoon and so. So Manabe sensei, you can see my acknowledgements there. So Manabe has motivated many Indian scientists. Krishnan worked there with him directly, and Professor Keshavamurthy, one of the top scientists, who was our director at IIT when I joined at a very young age. I mean, when my first beginning of the career. So all lot of Indians got benefited because of his knowledge, and then even now my student Feba, another student, where the first time we have done decadal prediction of the Indian Ocean dipole for the first time in the world. My PhD student, she published this paper in a couple of Feba Francis a couple of months back. This publication came, and some of these results we say that 10 years before there is chance of prediction of Indian Ocean dipole, which affects rainfall in India, Australia, Africa, and many places. But these are early times. But some of the signals of decadal processes, we can see this skill again. The thoughts. All this Manabe Sensei has done a lot of work. And from Princeton page, if you go and see, in 1960s, we developed a radiative convective model. Manabe's words, explored the role of greenhouse gases, CO2, ozone. This is the beginning of the long-term research on global warming, which I continued until now. And he talked of how the model development took place with KARUMURI. And this is a game-changing whole world, And then he talks of past climate even here. Don't forget about that. There is not everything is because of human intervention, but unfortunately now, we can say that mostly it's human intervention now. And he was Ehime Prefecture, 1931. He was born, and he got his BA, MA, and DSc from University of Tokyo, and lot of medals, Rosby Research Medal, name it, all the prestigious medals are there, and Nobel Prize has been there. Even without that, he was always a great scientist. All the climate community knew that. Now, it's sort of a vindication that he got the Nobel Prize in physics. And Krishnan's slides, there is so much of work that he has done. I would like to add his convective parametrization to this one as one of other points that we should see. And quickly, 1 or 2 slides on Hasselmann. Hasselmann has linked weather and climate. Weather is, those of you who do this, theoretical physics, particles moving in a fluid and all, you see these gases and all, this is sort of, mixing length and all, you must have studied in your theoretical physics. So weather is like, stochastic small particles, Brownian motion, but, they move randomly, but big particles have their own, defined path. So red noise, if you do your power spectrum. So weather will feed into this. Ultimately, climate becomes an envelope of weather. That idea, concept came from Hasselmann. Not only that, in 77, he used this stochastic model to predict sea surface temperature. Oceans are forced by wind, atmospheric wind. Wind is stochastic, weather. But SST changes, sea surface temperature changes slow. Based on that, he could predict that. And then based on all this one, motivated by that, we could, in late 80s, Ken Jibiak started predicting El Nino with using soft models. And now we can predict El Nino up to 1 to 2 years in advance. So this is, and Manabe also took inspiration from, and when he did soil moisture, he argued that that's similar to Hasselmann's SST winds. Here also he talked of high frequency, low frequency, associations. Okay, then climate change attribution is to Hasselmann. How you can attribute, make experiments with the model, that was again done by that, And finally, this is Manabe Sensei's recent photo in Princeton. His family, my boss, Professor Yamagata, shared it. He got it. Manabe, somebody sent it to Manabe Sensei or someone, so he shared it. Professor,
yes.
Can I show? There is 6-minute video of Manabe Sensei's video from Nobel Prize. Can I click it? Is it okay?
You may click.
Yeah. So that will inspire the students. Listening to him. It'll be great.
My name is Adam Smith from Nobelprize.org. Is it possible, please, to speak briefly with Professor Manabe?
Just a second.
Thank you.
Probably you'll have to stop screen
yes.
sharing. And...
Many congratulations on the award of the Nobel Prize.
Professor Ashok.
Yeah.
The video is not visible. That's not.
Sorry.
Not, video is not seen.
No video. It's only audio.
Audio, please. Perfect. Go ahead.
As I can hear, everybody is very happy.
I never thought that I received Nobel Physics Prize for the work I have done a long time, which I enjoyed very much, but it has been doing science of climate change. And when I look at all these four distinguished recipients, nobody received physics prize for my kind of work. And I really appreciate that the academic science to choose this climate topics of climate change, which I enjoyed very much to do throughout my lengthy career, which lasts more than 60 years. And so I am so surprised, but at the same time, I really appreciate that Swedish Academy of Science chose my research for this honor of this year.
I suppose they want to show how important a fundamental scientific understanding of the climate is.
That's right. Yeah. I think this one of the important things is understanding climate change. And what I did was using climate model which I constructed, changing one thing at a time, and just like a chemistry, do a chemistry experiment.
Yes.
I made a numerical experiment using this model, changing one thing at a time, thereby understanding how climate system works and how temperature change, how rainfall change, and why these changes result in the massive flooding which has been occurring near Beijing and in Japan, and all these massive flooding, and how this very frequent drought has been occurring all over the world. And I try to understand it using a climate model. Why this is happening? I think most important thing is understanding climate change. The prediction of climate change without accompanying understanding of it is saying no better than prediction of fortune teller.
Such an important topic, such an important problem.
Yeah.
And almost everybody agrees about the importance of it. But tell me, why did you begin to be interested in meteorology and the climate in the first place? What drew you to the subject when you were young?
Yeah, you know, it was, I went to graduate school of University of Tokyo. Then this graduate school of geophysics, I decided to focus on meteorology. At that time, the weather forecasting
Yes.
was more of art rather than science. Look at the past weather map and make
Yes.
forecast based upon the sort of a hunch and experience. But at that time, at Institute of Advanced Study, von Neumann, who is a pioneer of computers, among many other things, decided to do weather forecasting based upon laws of physics, which is a hydrodynamical equation, right? And so he started small groups and started studying weather forecasting. And this is the beginning of daily weather forecasting, which has become indispensable for our daily life.
Over your career, you've seen weather forecasting and climate prediction change from art to science. Amazing.
Yeah.
It's been a pleasure to talk to you, and my congratulations.
Hi. Hello.
Hello, it's Adam.
Okay.
Yeah.
Thank you.
Thank you.
Yeah.
And congratulations.
Okay.
Yeah.
I think.
So, okay. Thank you so much, Dr. Ashok, for
I
your.
think that's it. Yeah. So I think I will stop sharing. It's okay.
Yeah, that's fine.
Yeah.
You may stop sharing. So thank you so much, Dr. Ashok, for your very brilliant exposition of the topic on a very relevant topic of our times on climate change with reference to Professor Manabe's contribution. You have scholarly delineated the historical trajectory of his research down the decades. And we are deeply taken up the way, how he has committed his whole life. Not only Professor Manabe and scientists like Dr. Ashok, Hasselman, and all of them are committing themselves for a noble cause, a serious cause in the contemporary times. Well, you have introduced or presented the global climate model and also the stochastic climate model of Hasselman briefly. And more personally, I would like to appreciate your contribution, Dr. Ashok, especially the recent publication of decadal variability of the Indian Ocean dipole. That's sincerely appreciated. And thank you so much for this detailed exposition. Now over to the floor. The floor is open. Dear students, participants, delegates, and members of the faculty, this is a wonderful opportunity for us to engage in conversation with a scholar like Professor Ashok. Kindly unmute yourself and ask questions. Feel free to ask any question related to the topic. I would request Dr. K. Babu Joseph to give a brief comment to begin with. As I mentioned, Professor Ashok, Dr. K. Babu Joseph is the former VC, Vice Chancellor of Cochin University of Science and Technology.
Hello, sir.
And he's a physicist. Well, over to you, Dr. K. Babu Joseph. Then the floor is open.
I'm sure he knows about climate. QSAT has a very good department. Yeah.
We have a meteorology department at
Yes.
Atmospheric Science. So you may be familiar with.
All of them are my friends, Babu and Chakrapani, and
Right.
all very good friends. Chakrapani is a very good friend. Yeah.
Coming to your talk, I have appreciated your wonderful talk. You have been able to summarize a great deal of fundamental facts and along with the applications, the latest findings, reference to the Nobel Prize winning work and all that. It was a very good mix of both old and new things. But I would like to raise one question. Based on the studies of climate models, are we not heading towards a tragic end for our planet? What is in store for the Earth? Is it destined to die a heat death in a century or two? At this rate, it is irreversible. The temperature rise, carbon dioxide, the methane, all those things are the effects are irreversible due to man-made and natural causes. So, are we not heading towards the tragic end to all civilization, all life?
Okay. Thank you for your wonderful comments, sir. If I'm correct, the signal was poor, but you're asking what is going to be the fate based on the predictions and all climate change simulations.
Long-term.
Long-term projections. These are not predictions. We call them projections. Yeah. So if you go back to my slide here, I got one slide from here, the IPCC one. Just what let me share it with you again. Where is that? How to? Okay. Yeah. This picture, if future, you can see the range. This is sort of a summary of, there are hundreds of more, at least a few, if not hundreds, about 100 models must have gone there with different experiments by doubling the CO2. These are the set of temperature ranges that we see, and very low CO2. So what is this very low CO2? Whatever we have here, if we can stop here, probably it will go like this.
There is hope. There is some hope.
But the issue is, I have been involved in IPCC 2013, but more importantly, I have been also in the climate change negotiations. What you all know, Modi has gone and recently he has done wonderfully committed some of our emission, whatever India has to do. He has talked about it, and the issue is the policy makers. Lot of economics is involved.
Yeah.
No country is ready to unilaterally cut down. Mainly rich countries. They have been emitting since many decades, decades, but to cut down their emissions, they don't come forward. This is even countries like India with our limitations. For us, we can't suddenly stop, farming practices. You can't stop coal mining. But somewhere somebody has to do. The honest mainly lies in rich countries, and some of it, whatever we could do, poor countries are trying to do that. But everybody should do to the effect. In personal level, we should try to consume less. Otherwise, this is going to be, if you go to this SPM, summary for policymakers, this is temperature only. You will see the sea level rise, and many islands will go. And even countries like India, I mean, we are seeing extreme event, rainfall events.
Yeah, Kerala will disappear.
Yes, it will be costing. Of course, a lot of this accident, the heavy rainfall, a lot also is because of poor infrastructure management. But having said that, definitely there will be increase in rains and we'll be having troubles, more heat waves.
Yeah.
So that will cost us. We have to invest more in air conditioning, and even a poor person has to buy that. And again, we'll be adding more to the, emissions. So these things are, unless humanity, everybody should take this as important. But political, will has to be there, because suddenly if I say, okay, please stop farming rice, or let's close some factories, they will lose. This is a very tricky situation. It's not just for us. If you see 15 years back in Australia, they used to do that, and one person from UK has gone and he said, so that government about 2005 or 7, they were committed to climate change. They started putting tax on that. But somebody has gone there from UK and he said he was anti-climate change, and then the whole scenario changed. They lost. There is no other way. They had to go back to old practices. So this is a very tricky thing.
Very tricky.
Yeah, for example, you have to keep forests. And many people work, they poor people, they cultivate that. So their science has to come up, and we have to educate science and, humanities and policy makers. Everybody has to come up and educate people and provide them an alternate, solution. So this is all very challenging. Science that's why if you go to IPCC, working group 1 is only one science. There are 2, 3 adaptation and many other aspects we have to see, and there's a lot of scope for addressing this issue, but there is only a small window now.
Yeah,
I think it's a bit too technical and too much information for them.
If there is no other question, let me ask one more question.
Yes, sir.
That is about what we may call forestation.
Yes.
Program of forestation.
Yeah.
Planting more and more trees. That will help meet at least part of the challenge.
Yes.
On one side, but on the other, there would be increase in temperature due to what we call respiration or transpiration, whatever. Due to more trees adding to the tree cover already on Earth. So more jungles means more emissions, at least during night.
Yeah, that's a good question, sir. I am not an expert in that, but
Ecology,
several studies show that afforestation helps. It's a net effect that you have to see. One or two studies show that there is not so much effect, but definitely it causes a lot of improvement because of two things. One is your rainfall increase, you recycle the rainfall. Second is you're trapping. The advantage of forest is you're trapping the CO2. Their carbon sink.
That is an important.
That is the most very, very important. You're taking up CO2 and it goes inside. And if you see some of the slides in the Netflix shows, soil moist, soil conditions. We are tilling the, what you call as they help in managing the soil also. Trees hold the soil because soil degradation is there because of farming. But if you go for big trees and all, probably you don't have to do that. So that also helps. I mean, this is my personal opinion, but definitely there are a lot of advantages. But once you cut the tree, once it's died, it's carbon source. It's no more a sink. So the way to do is how to bring it into take the benefit economically by planting it. That's the challenge.
Even in Kerala, even in India, we can take up such a program. Not much money is needed for planting trees. Government can initiate.
Yes.
So I have some comment actually, it's not a question. Bhavja sir also will agree. When you really answer the generality correction to the planets, everything, there is something called the precision of a Earth also, right? Then the Earth is not moving the same path and again and again and again. Over a century, a slight change will be there. So I don't know some point of time whether that can also give some kind of effect. Maybe it is very difficult to see this time. So I think maybe there is some effect might be there because you not go the same path again and again.
Yes. If you
it may be too small.
No. If you see
small, but we don't know. The butterfly effect is there now, so we don't know that small effect.
But that is different. That is different.
Can I answer that, Professor Suresh? Yeah, if you, I don't know whether about 1 month back, my PhD student Charan submitted, he got his thesis. He has done these experiments, basically Holocene time. About in Holocene, the precision changes on thousands of year scales. So mid Holocene, there were changes because of the precision, small changes in precision and solar radiation change. Monsoon was very strong. He has made model experiments to show that how the Indian monsoon has changed. So definitely they are there, but they're on much larger scales, and they are relatively easy to, because once you change that whole, they are the basic drivers, solar radiation and precision. So it's relatively easy to show the changes. They're there, studies there. And chaos theory is something that's what you say, butterfly effect, that is more into uncertainty, stochasticity in the processes and all. But this, what you say, precision is more of a very, very well-defined red noise signal. So there will not be much of stochasticity there.
Well, there is a question from Swapnil Borges in Pune, JD Pune. At the personal level, other than planting trees and spreading awareness, what can we do to contribute for the reduction of global warming? So he's asking a very practical question.
Yeah. Swapnil, it's a question to you, to me, and to everyone. It's a nice question. So there is this one app from Pune itself, I think, this young girl who did it with her father. If I don't use my car today, how many kilos of CO2 I'll be saving? If I don't use my scooter, instead of 5 kilometers, if I walk, how much saving can I do? It applies to water also. Water we do, when you use the water, everywhere, water, I can switch off my fan now. It has been running, it's cold. It's become cold, so I can stop it. At every level, whatever we use, the so-called we use electric cars. Are we really saving? Definitely you're saving fuel, but where is the electricity coming from? Again, we're burning coal. So, idhar nahi, udhar nahi, jo bhi karte hain hum. Today I'm talking to you, and how many computers are running? So this is all, when we eat, when we sleep, every aspect there is there. Personally, all of us, we know that there is the signature of climate. Less is more, actually. If you can consume less, better it is. Yes, definitely electric vehicles are future, and there, if we can increase electricity, recycle renewable energy from wind energy and solar energy, this type of things. Even to some extent, nuclear is also quite good, but only issue with the nuclear is, after few hundred years, what would happen? So, but these are all viable alternatives. We should all think of wind energy and solar energy. And now the game changing thing is in the last 15, 20 years, technology has so improved. 20 years back, you would not have believed solar energy would have been, now we see so much of things happening. So I think those things have to be done in a bigger way. And all of us should try to, and personally, I think most of us use cars and scooters. For the beginning, we can reduce that and use bicycles. I do that once in a week. I walk once in a week. I bicycle to university. And so all of us can do. It's good for health also. Not only here, you go to your friend's home. Why don't you go on a walk? So then, this goes endless. I'm not an expert, but all of us, all of you, me, everybody knows, and we should educate our friends also, if possible. If you're going together, let's say, okay, let's walk together to the movie. Why not?
Could you see Andrea's question in the chat box? Or I'll
rapid variation of temperature in Arabian Sea resulting, Professor Prasanna's work. How does this rapid temperature difference occur? So this is, temperatures globally, temperatures are increasing. I don't exactly recall how the any papers and special warming in Arabian Sea, but definitely seas are warming. What happens is, if you understand the tropical cyclone formation, there is what is called as, for convection. Those of you who are studying convection is non-linear. So till 26, 27 degrees, there is no convection. But suddenly, if your temperatures increase beyond that, convection triggers. So that is one of the source for tropical cyclone formation. About 5 conditions are there. And from 26 to 30, 31, your cyclone intensity will increase. So for a tropical cyclone to form, you need a warm sea surface temperature and deep enough mixed layer and initial perturbation, disturbance, and low vertical wind shear. What happens is during monsoon time, you have strong vertical wind shear. So that's why cyclones don't form, but monsoon depressions do form. But on the other hand, what is happening is if your temperatures are increasing, this is all in a sense, you are getting more energy pumping into the atmosphere. So if the shear is there, but there is so much of energy, it's not getting mixed up. And that's why Arabian Sea was relatively, it's not, as compared to Bay of Bengal, the temperatures and all and other factors were relatively weak. But now Arabian Sea is also warming up. So that is playing a role, major role. But all said and done, Bay of Bengal is still the place where you will expect more and more cyclones, and Arabian Sea also things will increase. So you can check the paper. That's why Professor Prasanna is a very, very eminent oceanographer. You can see those papers and understand. Okay, Andrea, does it make sense? Is it clear? Then Cristiano, yes. Can we successfully implement all these ideas?
That's a question.
Can you, Cristiano? Will you come to college tomorrow by walk? Or go to the shop or go to movie? This is a question for everyone. We should. To the extent possible. Don't worry. Don't think of doing 100%. Try doing 1%. Do it once in 10 days. Then increase it. Go to 1 kilometer to the neighboring shop or to friend's house. Then increase it. It can be easily done. It's not, you can't do everything. But if everyone cuts down his car one day, imagine if I come to office and go, I'm burning 1 liter. And if I stopped it, I stop this one liter of my, petrol and what else? CO2. Oh, you should ask this question to a geophysicist. Maybe tomorrow. Yes, crackers are bad. Definitely. I agree with you. Yes. But at the same time, I was telling you the policy versus science. There is a lot of people who depend on these crackers. In Tamil Nadu government was exhorting all the politicians not to stop, other states not to stop buying. Definitely, as a chemist, if you do chemistry, you can produce something which can produce less smoke. And smoke is dangerous for health also. So there are dual benefits. If you can reduce that, one is you are not producing too much CO2, climate change, and many of the benefits, these are what is called as co-benefits. So sometimes, you want to reduce global warming, but you will be reducing air pollution also. Definitely, you can do a lot of things.
One more message from Elson.
Elson, again, if you see the slides, the temperature will go up, and you ask any medical scientist, you know, that wait for this adaptation 2, WG2, it will come in IPC. You go to ipcc.ch, there you will see all these reports. Now IPCC 2021 ka report aaya hai, science ka. If you go to 2013, you will see already other reports. And effects are there. You know, we already see a lot of newspaper reports. Animals are dying, and the shifting of, you know, phenology, crop phenology. You can see Arctic and Antarctic. Some of these, you know, the changes, temperatures are changing so much. You can see some green shoots, and farming belts are changing, and those dragonflies and all, which were seen in some certain place, you can see them somewhere else. Birds are migrating, and many animals are dying. Not just because of our consumption, but they are unable to survive. Many, they say that, you know, lakhs of things are, if not lakhs, thousands of species have already gone because of climate change. So this is another aspect.
Any comments from other students, or even Dr. Jijo or Dr. Lijo or other members of the faculty of SP College? Well, Abhay is asking another question.
Yeah, Abhay, definitely, as long as you are not it's mathematics, Abhay. Yes, if you are doing one, if I'm using electric vehicle, I'm not producing CO2, good. But when I'm charging my car battery, how has the charge come? Is it because of CO2 burning coal? If not, very good. If I have burnt coal, what is the net? I have saved some X amount of CO2 here. I mean, production. There, a certain amount of CO2 has been used. How much is it? So it comes to net. I think definitely these are good in long term, because new technologies, as we go to solar and, you know, wind energy, etc., more and more electricity will be produced using these things. Then charging will be better, and also the efficiency of the batteries. You see a lot of technology, the opportunities. Whatever I talk is climate change, but you see, for example, somebody asked about the crackers. So I talked of chemistry. Here, designing of batteries, you know, saving, how to produce electricity cheaply and from other sources. There's a lot of your generation can think of all these things. What can you do? Stopping electricity is one thing, but can you have the cake and eat it too? You produce electricity so cheap that you can use all these gadgets and you don't produce CO2. That will be the best scenario, right? So can you do that? I mean, this is the opportunity for most of you guys. These are actually business opportunities, future career opportunities for you. And water is something, again, if climate change or not, all of you know how important water is. We all have to share, store water, groundwater use. What happens in climate change to groundwater? People do, but, you know, these are all questions. You know, we indiscriminately use the groundwater. After that, what happens? These models are not yet at that stage where, but this is one topic, and there are a lot of questions. We plan to, you know, link the rivers. How safe is it? What are its long-term repercussions? There is always, whenever there is an economics, there is a repercussion that would happen. You have to see that. Similar thing is your electric vehicles. It's a question of budget there.
Yeah, I think right. Thank you, Dr. Ashok. And I think prior to Irene Saji proposing the word of thanks, I just wanted to make an observation. I was just listening to your talk, and the climate change, you know, it encompasses a good number of disciplines. The methodology itself has become so much interdisciplinary today. That's another insight which we draw from this lectures.
In fact, we have biology. We have biological models, because
mathematics, statistics, physics, and chemistry, definitely biology. Then which are the other disciplines actually?
Everything, you know, biology with biology, because CO2, 50% of the CO2 is in the ocean. So how do you trap that? So you put the equations, but how is this CO2 synthesized? You know, phytoplankton, zooplankton. So biology is there, chemistry is there, physics is there, economics is there. Because how do you say the profiles that you see, how much of CO2 is being pumped? Right. It's not random. Previously, they used to do randomly, but there are trajectories that economic models are there. People build that. So that is there. And one of the biggest thing that has to come in is that, you know, model technology, new technologies, human consumption. Suppose of course, it's very challenging political. I mean, it has political ramifications in the sense country level. A country like India, there are a lot of people. So if I can put the effect of food that I'm eating mathematically, what I'm consuming, because ultimately it's also heat source and heat sink, because agriculture, we do agriculture and all, but how much of I'm producing, how much of I'm eating, how much of it is being wasted. So these things can also go human action more directly. It can be put, and traffic, travel, anything we do, chemistry, we still don't, these are all parameterizations. Can you improve the modules and make them computers are another issue. World's fastest computers are being used. So we use CPU based systems. People think of making it GPU and parallel programming. And another thing is full mathematics, how you solve this partial differential equations. We use finite differencing as Fourier and spectral methods and finite element. There is more, fresh blood has to come think mathematically how to solve these equations with less error. Professor Suresh talked of stochasticity, butterfly effect. Any small error in the initial conditions blows, and your weather forecast also, after some time they go. So these type of things, there's a lot of opportunity for mathematics also.
Yeah.
Computers.
Excellent. Thank you so much. And I think I should stop asking questions, but I have one more question. That is, the students of different disciplines are attending this webinar. Well, physics students from SB College and those in mathematics in other branches of sciences. Do you have any suggestions, especially those who would like to specialize in the area of climate sciences or anything of that kind? And second, as an inspirational factor, what's the most recent project or the contemporary project which you are involved in?
Okay. Opportunity wise, what we do in our department, this is the first department in country, or maybe first or second, I don't know, where atmosphere and ocean together are taught in one course. MSc Ocean Atmospheric Sciences, that's our degree. And many universities like Andhra University, Cochin, they have been traditionally offering MSc Meteorology and MSc Oceanography, then MTech Atmospheric Sciences. Then several IITs are offering all these courses. So if you are interested in the hardcore climate and weather sciences or ocean sciences, you are welcome to come and join here. But as a research career, I see a lot of, and now of course, weather forecasting is there. Now private companies are also coming. And in climate change also, there is a lot of opportunity. Just now I have told you the science part of it. But since 1992, climate change negotiations are going on. I have been very intimately involved for 5 years as a policy maker, as a senior scientist from IITM, as a deputy head of climate change, I was deputed. So lot of economic, discussions and negotiations are there. Climate policy is there. And in future, these things may feed into law also. In fact, already it's there. Whatever negotiations we do, climate change, Kyoto Protocol, and now new laws, lawyers also will have an opportunity. Climate and environment, not necessarily just climate, but climate and environment. And technology, engineering, how do you, crops, paddy, can you design a paddy or something, which is resistant to, many people already do that, but from the point of climate change, can something use less water? Or will it be able to withstand a certain range of temperatures? So this is agriculture. And etymology, what happens, what type of pesticide, what you call as pests would come if the temperatures increase. There is biology in addition to carbon cycle and all. So these are some of the many opportunities. Even we don't have to think. If the students sit and think, they will get so many ideas better than us. That's one. Second is what we do is after coming to University of Hyderabad, we started, I was leading this system climate model development in India. First model was developed by me, and second phase was this IPCC generation. They have added aerosols and all. Krishnan's group, Dr. Swapna and Prajesh, they're all from QSAT basically, Swapna and Prajesh. So they have done that system model. It's working. So model development and all. But after coming here, what I have started is, coming to universities, I interact with a lot of students. I do a lot of things I wanted to do since many times. One is the past climate simulations. Also, the first climate group in India, which does model simulations of past climate. Many people do that using observations, but we are using models. And then I also use climate change, climate and weather predictions for crop yield forecast. then decadal prediction that you have seen. And two other projects that I do is one is the river discharge into, what happens, when, river discharge effect of El Nino and Indian Ocean Dipole, etc., and river discharge, and how it affects the ocean biology, what you call as the biology in the Bay of Bengal adjacent to River Godavari, using models. So these are several topics that, and of course I do theoretical work, instabilities of monsoon, pure theory, much before models have come. Understanding them is very important because they can give you large scale indices to improve your prediction.